let me just start out by saying two things. One, I have often had to follow excellent speakers and found that a little intimidating. However, I have never had to follow something as truly awesome and spectacular as what just happened here. So, gosh, Ranjit, you did not tell me that that was part of the deal. So that was number one. And then number two is this is one of the more intimidating talks I've ever had to give because I am not a programming languages person. I have had a lovely time here. I know many of you, but it has felt like stranger in a strange land. So it was a little challenging figuring out exactly what I was going to talk about. On that note, ideally we'll have some fun here. So I do systems, and I do systems construed broadly. And when this field started, which was even before I was around, I'm not quite that old, we were like all one big happy family. There were people who did hardware, and there were people who did software, and there were people who did programming languages, and we all talked to each other, and life was wonderful. Unfortunately, over the last 50 or 60 years, we have fragmented into a gazillion different communities, and this isn't even all of them. And one of the messages that I want everyone to take away, in particular students, is that you don't have to stay in a little box. Okay, there are lots of little boxes there, but in fact, many of the more interesting problems occur at the boundaries between those boxes. So that's one thing, and if you get that, you can just sort of leave. So you could argue that I currently work in like all these areas, and you know, some to a greater or lesser extent. Now, you might be tempted to go like, ooh, wow. Yeah, please don't. Because the reason that I can work in all those areas is that I have an amazing group of collaborators. So, you know, how can someone like me actually do something that might be considered programming languages? Well, it's because like Steve Chong used to sit down the hall for me and we could talk about things and we could co-advise students. And a lot of this talk is really about the case for collaboration, what makes a good collaboration, and perhaps a way to a kinder and more gentler world for all. My impression is that the programming languages community is actually more kinder and gentler than the systems community. And so if you could like all go home and talk to somebody in the systems community and say like, why are you guys so mean? That would actually be helpful. So that's a little homework assignment for everyone. Now, these are my collaborators, but in fact, you know, I have this massive team at UBC. They are awesome and wonderful, and I have literally 10 undergrads working in our lab this summer. And none of this work would happen without the students. And then I also have this other team that was finishing up at Harvard, so those are all my final PhDs. Michael and Crystal, the first two, just graduated last month. David graduated the year before. So this is going to be a talk in 3 parts. I want to thank Emery for setting this up beautifully. He talked about narrative. I'm going to take that idea of narrative even further, because when I teach my graduate OS course and I teach people to write, I make them tell fairy tales. And I make them cast both existing papers in terms of fairy tales. So I'll be teaching this course in the fall, and when they do particularly good ones, I tend to Facebook them, so please join us. Some of them have been brilliant. And a fairy tale has 4 key components, right? There's the once upon a time, which is context setting, and then there is a villain. This is the problem you are trying to solve. And then there's a hero, and the hero solves the problem. That's your solution. And then there should be a happily ever after, which is like, why should anyone care? And I would argue that every good research paper must follow this paradigm, and I literally make the students tell me what their fairy tale is. They love me for that, as you might imagine. So I'm going to talk a little bit about collaboration to get us started, and then I'm going to talk about how that collaboration has manifested in a couple of projects that I've worked on, and then mostly what I'm going to do is tell you all the hard problems that I need you folks to help me solve, because I can't. Right? So I will demonstrate that this collaboration does not mean I'm an expert in any of these, but that I really like to work with people. And there are 2 ways that we can solve these problems. One is, like, we can talk and we can work together. And the other is you could just go off and solve them and tweet when you're done. And that would also be fine. So this is going to start with my collaborator, Cynthia Rudin from Duke. So Cynthia is a brilliant computer scientist, statistician, and mathematician. And she works in the area of interpretable machine learning. So what on earth do we have to collaborate about? Well, once upon a time, Cynthia came to give a talk at Harvard. I was still at Harvard. She was at MIT. And she talked about how she was using Markov chain Monte Carlo to produce really good rule lists. Okay, just like facts here. I had no idea what a rule list was before her talk. Had a somewhat understanding of Markov chain Monte Carlo, although didn't necessarily understand all the math behind it. So if you don't understand those things, that's totally fine. The talk will work still. So we're talking in our little one-on-one after, and she wistfully says, you know, we really need to make this scale to bigger data sets. I said, oh, well, that's really interesting, because I have a student that I'm co-advising with Ryan Adams, a machine learning person, and she's actually been working on ways to parallelize MCMC. So maybe there's something we could do together. So this sounded too good to be true. And so there was our once upon a time, but you see there was a villain here. And the villain was that, you know, I now knew about rule lists for all of about a minute and a half. But there was actually an even bigger villain, which is that in her talk, I really hadn't understood any of her math. And the biggest villain of all is that I was really, really bad at saying, like, I don't understand that. Now, I'm not going to ask anyone here to raise hands, because none of us are going to do it. But I just want you to think for a moment, have you ever been sitting in a talk, or even having somebody tell you what they're working on, and you nod, and in the back of your head, you're going, I haven't a clue what they're talking about. I don't understand. Okay, I have done this. I have spent the better part of my career doing this. And my takeaway for today is, let us all stop. Okay, this syndrome has a name. It's called imposter syndrome, right? You're thinking, I'm supposed to know this. And if you're a first or second year grad student, you're terrified because, like, everybody else knows this and I don't. That's not true. And the problem is that as you get senior, it gets even worse, right? It's like, I'm supposed to know this, so I just have to act like I do. You know, and it got to the point where people would mention names. And even if I had no idea who they were talking about, I felt like I had to, because otherwise I was like disrespecting somebody really important. It's like, actually, you don't have to, right? So this problem is that imposter syndrome puts us in a cage. And so the question is, like, we all know this exists, and it hits us at different stages and in different ways. So how do we get out of this? And so I am going to claim that the way you get out of your cage is what I like to call the stupid question. And to be fair, they're not really stupid questions. They are questions of naivete. But they are the questions that we are terrified to ask. And we need to start asking them. So, how did this sort of stupid question thing happen with me and Cynthia? So, it starts from a really, really simple statement that's hard to utter, which is, I didn't really understand that. I'm sorry, what did you say? What? I didn't really understand. I'm sorry, I still can't hear you. You know, I really didn't understand that. Like, how many of us find that a super easy phrase to say? Yeah, that's what I thought. Okay. And the beauty was that Cynthia would say, oh, well, let me try to explain that again. It's like, well, that was really nice. And then she'd explain it again, and it's like, I'm still kind of a little fuzzy. And she would patiently explain it again. And there was never any judgment. There was an assumption that we were both like smart people, and we talked different languages. And so all of a sudden, we had this happily ever after where both of us could be free to, like, point out the things we didn't know and ask stupid questions. And the beauty of the stupid questions is that every once in a while, this outside perspective or this naivete would uncover a really, really interesting or important fact. So in the 4 years that I have now been away from Cambridge and she has been at Duke, you know, the one constant in my life is that every week there's at least one meeting with Cynthia and her students and my students, and we talk. And, you know, I will ask what I think is a stupid question, and she'll go, oh my God, we can use that like to prune a search space. Okay. You know, and we've literally sat in code reviews together where we'll be going through the code and she'll say, I don't understand what that calculation's doing. And we'll talk through it and suddenly realize that, oh, we can speed up the code because we don't have to do it in that way. And we've had code reviews where we improved performance of machine learning algorithms by a factor of 4 in a 2-hour code review. In Python. Like, who does that? And neither one of us could have done it alone. And I think that's really the message, is that an effective collaboration has these qualities of this total safety, right? I can ask a question and it will be taken seriously and answered as opposed to made fun of. Number one, and then number two, that you sort of bring out the best in each other and are able to bounce back these ideas. And that you really embrace these questions by saying, is there something actually fundamental here that we should be addressing? So that's kind of the vague picture. I'll start out with a problem that we worked on together to give you a sense of the kind of work and some of the problems. I like to call it the problem with ML, which I want you to solve. Okay, so good news. The ML are all the cool kids. They get all the notoriety, and you are going to save them. Yeah, okay, good. So what is the problem with ML? The problem with ML is that the work I do, and a lot of work in the field, really combines 3 things. There's a bunch of theorems. You have to have fancy equations in Greek letters. Who knew I would ever write papers with? Anyway, so you have to have theorems, and then you usually have algorithms, and then you have some code. Now, this begs the question, like, does the algorithm properly use the theorem? And does this code I'm releasing actually do what the algorithm says? Now, it turns out, this will come as a big shock to this community, but not everyone uses great software engineering and coding practices when they do research. Oh, Dolores, really? So the first time, like, we were getting a paper ready to publish, I uttered the phrase, like, so have we tagged the repo with the version of the code that matches the paper? And I get this sort of, like, deer in the headlights. And this was one of my own students. And she's like, well, you know, we've run some of the experiments on different versions of the code. And I'm like, we what? And I said, well, I know what we're doing this weekend. And they look at me and they're like, what? Like, we're rerunning all the data for the paper. Like, we are? And I'm like, yeah, you don't release results that aren't from like a single snapshot of the data. Like, that's considered baking the results. So we actually have to rerun everything. And I suddenly realized that this was not common practice. So I came up with these 2 theorems about machine learning. And I thought I was being like a snooty little systems person, you know, being mean to the ML community. But in fact, every time I have stated these to my colleagues who do ML, they kind of nod and go, yeah. So here are my 2 theorems about the problem with ML. I know I'm being recorded, and this is really terrifying. Don't tell any of your ML friends to watch this. But theorem number 1, every paper for which there's an algorithm and an implementation, they don't match. And all the ML people go, yeah, that's probably true, okay? Theorem number 2, there are a bunch of ML papers published in really prestigious venues touting techniques that fundamentally don't work, but there are bugs in their implementation that make it look like they work. And that's the one that terrifies me when my ML colleagues go, yeah, that's probably true. Right? Like, this should be terrifying because there's like all these life-critical things we're using AI and ML for. All right, so this is the problem with ML that eventually I'm going to get you to help me solve. So to do that, let me tell you a little bit about optimal and sparse decision trees. So this is my team. It has folks who are now at CMU and University of Toronto and Duke and everything else. And we have this incredible distributed collaboration even before COVID. So here's the problem. You have some data. And in our case, it's binary data. You can take continuous data and make it binary, but we're going to ignore that for now. So you have a set of samples. And each sample has a set of features, and then each sample also has some outcome. So in this case, it's a binary outcome that you're going to predict, yes or no. And the problem you're trying to solve is we would like to construct the best sparse model we can that describes the data. So what kind of models? We're building decision trees, right? These are like if-then-else clauses. So, and what do we mean by best? Well, we're going to optimize some objective function, so like the accuracy of the model. Did I just lose my sound? Okay. We're going to try to optimize the accuracy of the model, but we want to favor sparse models, so models with few leaves. Now, why do we want to do that? Well, because we do interpretable ML. And the idea is you want to be able to hand somebody a model that they can look at and understand. Now you say, why? Deep neural networks, like everybody knows those are way better. But how many of you, let's do a little poll, you go to a doctor's office and the doctor says, type, you should take drug X. You say, oh, okay, why? They say, because it said so. How many of you are going to go right out and fill the prescription for drug X? I'm probably not. Right? On the other hand, if they say, well, because you are, over a really big number, Margot, and you had your hip replaced 5 years, whatever, here's a bunch of decisions, and because of that, we want you to take drug X, I am more inclined to actually trust the doctor. So there are actually lots of applications where people want interpretable models. So that's what we're trying to do. So here's a little example. How do you decide whether you should take an umbrella with you in the morning? So we have a bunch of different people, and the first question you say is, are you in San Diego? And if the answer is yes, then you don't bring an umbrella. If the answer is no, then you ask other questions. Of course, there's another model that's almost equally as accurate, which starts with, are you in Vancouver? And in that case, the answer is yes, you bring an umbrella. Okay, so why is this a hard problem? Well, it turns out the search space is enormous. This is an NP hard problem trying to find the optimal model. And so when I tell people what I do in machine learning, it's like, oh, we solve NP hard problems to optimality on laptops. We actually do that. It's kind of cool. You could not do this 30 years ago, even with all our techniques, but today you actually can do this. So what's the secret sauce? We use a dynamic programming formulation with bounds. And this is where, Cynthia's mathematical brilliance comes in. So we have thousands of these, not thousands, but we have all these really interesting bounds that tell us how we can prune the search space by saying, there's no way the optimal solution can actually be any descendants that look like this, so we don't even have to look at them. And that's how we managed to solve this. All right, so that's the context. Now I want to tell you, what does it look like to do a project like this? So Cynthia will have a good idea we can optimize accuracy. What happens if we have imbalanced data? There are many more true answers than false answers. Could we do a balanced accuracy? Ooh, that's a good idea. Let's do a bunch of math to figure out whether we can still prune the search space effectively. And so we do some math, and then maybe we write up all the theorems and stuff in LaTeX. And I'm going to come back to whining about LaTeX in just a moment. Just a little heads up there. So we do a bunch of math, and then, once we think the math looks pretty good, we'll go ahead and we'll do some prototyping in Python. And then, you run some experiments. And depending on how the experiments come out, you might go write some more Python. You might go back and do some more math. Or, because we like to make stuff run really fast, we end up rewriting the whole thing in C++. And then we do some more experiments. And then we might have to go back and do more math or change the C++, and then we write stuff up. So here's a probability question for you. At the end of this process, what is the likelihood that the math equals the Python equals the C++ and is the same as what we're writing in the paper? Approximately 0, right? And just as an example, a project we're doing this summer is that we're trying to take one of our our first algorithm for optimal decision trees, so our simplest algorithm in our Python implementation. We said, what if we could rewrite it in a proof language, and then we could prove that we're doing some of the right things. So we decided to do that in Daphne, and we can argue about the right language. We decided to do it in Daphne. And so what happened was we took the team and we started going through the paper line by line, right? We wanted to make sure we understood absolutely every theorem. We found bugs in the paper. Shocking, isn't it? You know, you have to remember, those of you who haven't published in ML papers are 8 pages of paper and then like 50 pages of supplementary materials that have all the proofs and everything else. Now, these were not fundamental errors in the algorithm. So far, we have not found fundamental errors in the proofs, but there are notational problems that are just wrong. And that if someone were trying to, oh, I don't know, replicate our work would have difficulty because the numbers are wrong. So why are we going through this with a fine-tooth comb? Why isn't this just a straightforward port? Well, because actually going from like a normal programming language like Python or C++, in this case Python, to Daphne is really hard. Right? It's not just a code port. It's not just rewriting functions. It's really rethinking the whole algorithm from the top down and figuring out how to express it. So even at the end of the day, when we succeed with this, which I think, I don't know, I'm hoping we will, you know, will there be any assurance that this new implementation is the same as the old implementation? Probably not. So what is it I want from you? So this is part 1 of problems I think you should help me solve, or that you should just go off and solve and send me a tweet. So I actually want a way that I can combine something like a proof language with my paper, right? So the fact that I write theorems in Daphne and then I also write them in Python, in LaTeX is a bug to begin with. Right? Why do I have to do this twice? Because as soon as I have to do it twice, it's wrong. I want to be able to generate code like I can do in Daphne. I actually want that code to be really efficient, and we want to actually give guidance about how to make it efficient if the language can't figure it out for itself. And I really want to make sure that all these things match. And I don't think there's a way to bring that all together right now. And you might say that the LaTeX part and the paper writing part is like not useful, and there are solutions to little pieces of this, but there isn't an integrated way to do this that really lets me assure that all the things that are part of my problem are actually there and correct. So that's one problem I'd like. Now the other problem, and this is one I don't really have any clue how to tackle, but it keeps me awake at night, and I've been trying to convince students to work on it even though I have no idea how to tackle it, which is ML is all about stochastic algorithms, right? How do you debug those? You don't. You run them, and if they look good, you assume they're correct. Like, it's really kind of terrifying. But debugging stochastic programs is a really, really hard problem. And I forget who, I feel really bad. Somebody suggested this. Oh, actually, it's Burke Uston, who's at UC San Diego. We were chatting. We do some collaboration. Being able to generate, like I would like to specify what I want in a synthetic data set so that I could run my algorithm and know it was giving me the right results. That would actually be a fabulous problem, right? So how do I describe what I want the data to look like? And then given that description, how do I compile that language into a data set that I can then use to test my algorithms? Like that would push this field forward enormously. So there's a problem I'd like your help on. And then here's my LaTeX rant. So you can feel free to tune out for 30 seconds. Why, in 2022, do we not use a good why do we not have a good WYSIWYG editor for writing papers? Right? The rest of the world uses WYSIWYG and can see what they're doing. And they don't spend 45 minutes figuring out how to get figure 4 to appear where you want figure 4 to appear. Why? Like, is it really that hard a problem? So we need something better. Like, this is not a good use of our time. How many of you have ever spent time fighting LaTeX? Everybody. How many of you enjoyed spending that time fighting LaTeX? I need to talk to you people. Okay, so these are the kinds of problems I would like your help with. And in a late-breaking related problem, I spent Friday at the ACM 75th Anniversary Symposium. And there was a session there about balancing trust and risk. And Brian Ford made this really great statement that was essentially, I summarized as, ask not how to make people trust your technology, ask how to build technology that people trust. And I thought that was a really insightful and correct way to view this problem. And so this turns into a language problem, which is how do we describe what a system is supposed to do in terms of accountability, right? So it might mean in terms of government regulation or privacy or security properties or all these things. How do we state that in a machine readable way? And then how do we verify that in fact a given system actually subscribes to that? So I think this is actually a grand challenge problem. So I don't expect you to tweet it in the next month. But I think that is a grand challenge problem that will require expertise from a lot of different sources. So stay tuned for that. We might be holding a workshop on accountable systems in the near future. And if you're interested, let me know. All right. So that's sort of the kind of things I do in the ML space and places where I want your help. So now I'm going to go into dangerous territory because this is actually like stuff you folks do. So this is terrifying. And so this is the road from operating systems to program synthesis. So once upon a time in 2004, when cloud stuff was becoming like real, but we still lived in this x86 monoculture, my staff research person, David Holland, and a visiting student, Ada Lim, who is now both an MD and a lawyer. Yeah, she's one of those real underachievers. Anyway, we had this crazy idea that one way to provide security in the context of this monoculture was that if you could randomly generate new architectures, okay, so new ISAs, and then synthesize the virtual machine for that architecture and the operating system and the tool chain, then what you could do is your cloud deployments would no longer be a monoculture. They would be a collection of virtual machines all running different architectures, and this would be a higher barrier for people to attack. And so we thought this was kind of a cool idea. Now, given an ISA, synthesizing a VM for it, not that hard. There was a lot of work our colleague Norman Ramsey had done about synthesizing the tool chain, but there was this pesky little problem of actually synthesizing a brand new operating system for a brand new piece of hardware that seemed like a really interesting problem because like we did operating systems. So that was 2004, and as you might imagine, getting anybody to fund this, what I like to call fringe lunatic problem, was impossible until 2015 when DARPA came along. So DARPA did not know they were pitching us a project. So DARPA started this BRASS program, which was about software sustainability and evolvability. And what they really meant was like, if what you're trying to do changes, how do you make the software adapt to those changes? But we have fantastic colleagues at Charles River Associates, and we convinced them that if software had to evolve, then it was equally important that we be able to evolve in the presence of like changes to the hardware. And if you were going to have changes to the hardware, well, then we had to synthesize this tool chain and this operating system. They were like, yeah, that sounds really cool. So we were total fringe lunatics in this. And now we get to one of the true confession parts of this talk. So in 2004, when we started doing this, in my head, like the synthesized operating system was sort of, you know, it was like a template, and you had like pieces you plugged in, and it was really just compilation. And it wasn't actually going to be that hard a problem. Imagine my surprise in 2015 when we need a programming languages person to do this, and I suddenly learned that there's this whole field of program synthesis, and people are actually synthesizing programs, and it's no longer an OS problem, it's really a PL problem. It's like, oh, well, that's exciting. But like I said, collaboration is great, and so I brought Steve Chong with me on this insane journey, and we actually built a system to synthesize machine-dependent portions of operating systems. We did not succeed in synthesizing an entire operating system, but we did actually build some synthesis tools, and we got it to work, and you could plug those modules into an OS, and it actually ran, and it was pretty cool. You know, remember, the great thing about a dancing bear is not how well it dances, but the fact that it dances at all. Okay? This was a dancing bear project, and the bear danced. So what did we learn? Well, we learned the lessons that you can learn in any software project, which we all forget. So just a reminder, 1 miracle per project. We had like 15. Not great. And also, we spent a lot of time developing and building before we spent a lot of time actually testing each one of those things. And I think the, test early and often is easy to forget sometimes when you're really excited about what you're doing, but it pays off if you do that. But some more domain-specific things we learned is that operating systems have both machine-dependent parts and then machine-specific parts, right? So what do I mean by that? No other processor in the world does, recapitulates phylogeny, i.e. the x86 architecture, goes through all the states of its evolution when it boots. No other architecture does this. This is a very architecture-specific thing. And there's no way you want to actually try to synthesize most of that, which is unfortunate. But fortunately, most processors aren't like that. There's another problem that sometimes writing specifications or the specs are longer than the code. In our case, if you actually are going to do a lot of ports, that might be okay. But sometimes the specs are really long and ugly, so we need help there. But the really important lesson that I'll take into our next project that I'm only going to talk about really briefly is that this, synthesis is really a spectrum, right? There's compilation, there's synthesis, there's magic, and there's lots of places on that spectrum. And if you want to build large complex systems, you need to pick and choose from among those. Interfaces matter a lot, shocking. And generating assembly language is really hard. So I'll just whine a little bit. So we try to get smarter when we learn things. And so when I moved to UBC, I decided we were going to try a really different approach. So still a hard problem. But when you have awesome graduate students, and in particular, this is Jerry, and Jerry loves nothing more than studying up on the newest features added to C++ and figuring out how to use them to write really, really fast and flexible code. So Jerry, for his master's thesis, wrote a build your own operating system. And so what this is it's a set of operating system modules. So low-level things like schedulers and context switchers and, RPC primitives. And each one of those is highly configurable. And the idea is that given a particular application, you can assemble the right operating system for it. So our target domain was sort of like little IoT devices, right? We wanted to start small. If I learned nothing else from the previous project, which is called Princess, by the way, it's a great acronym. I forget exactly what it stands for, but you can imagine all the fun we had with crowns and things. So, if we learned anything from Princess, it's that retrofitting synthesis into an existing operating system was just really crazy. So what if we could start to build an operating system that would be more amenable to synthesis? So that was what I wanted. And what he wanted was a system that could actually build these tiny operating systems for IoT devices. And so we're both happy. And so the big picture is that, an operating system kernel is a set of these kernel modules, but each of those modules is actually represented by a set of components, and the components themselves have like lots of teeny tiny building blocks. And so the way you build a kernel is you just specify your module, which components it needs, and you sort of parameterize which building blocks you want, and voila, you get a kernel. And it's really cool, and it works, and we write little applications to like do plant watering systems and stuff like that. All right, so the magic sauce that he used is he said, look, in a perfect, well, software engineered world, we would use all these virtual functions, and then it would run really slow. And so instead, and he came up with this without knowing this 2004 history of like, we should kind of have templates where we can drop stuff. Anyway, he ended up with template-based programming and then uses C++ concepts to make sure that you can mix and match the components without getting type errors. Super cool, actually works. So this leads to my next set of problems. So here's where we are. We have this little tiny system that, to some extent, we designed with the goal of synthesis in mind. So now I have a bunch of different synthesis problems. So what I want to do is I want to specify the requirements of a kernel, and then from all these building blocks and components, just synthesize the kernel. And so, the scale of this, our kernels range from about 80 lines of code to maybe 120. So they're not huge. They're extraordinarily modular. But I need a way to specify the requirements of the kernel, and then I need a way to actually do the synthesis. So that's a really fun problem. ISA specifications. So in the Princess project, we built a specification language. I'm not sure it's the right one. Hardware vendors are starting to give us specifications of their ISAs, and that's great, and we should encourage them. So another take-home assignment, when you talk to people who do hardware, it's like, yes, we would like specifications of your ISA. That will make all of our jobs easier, not just mine, but yours too. And then I need to do this like hierarchical specification, because once I have the specs of the kernel, I also need to be able to specify all my little components. And so these are sort of different kinds of specification languages. And then, you know, the systems geek in me is like, can we do any of this without sacrificing performance? Who knows? There's a bunch of variants on this. So I sort of call this higher level synthesis kind of stuff. And you know, I run into this because I want to build these operating systems, but another one of my former students wants to do some stuff to make microservices faster, and then wants to evaluate it. Well, how do you evaluate like a whole suite of microservices? That's really hard, because what you really want to do is you want to be able to specify different classes of microservices, and then within each of those classes, randomly generate programs that are representative of those classes, and then wire them up in certain ways. Now, you could build this all manually, but so much of it is going to be cookie cutter and boilerplate that it seems like this is a prime automation target. And so I think this kind of higher level synthesis of being able to assemble components and put them together is actually a wide open space. The other place I want this is in the security context. So if you've ever worked in security and have to do an evaluation where you show how effective your intrusion detection system is, the evaluation is impossible, right? There are no good data sets out there. It's really hard to create a good-looking attack. Surely there must be a way where I could describe what I want in an attack, and we could actually synthesize software that launches those attacks, and then I could build intrusion detection systems and actually evaluate them. This would have a huge impact on the security community. We have a framework that would make it easy for you to run those things. So if anybody wants to work on this, I think this is a really huge problem. And my former student, Michael Hahn, would probably be an interesting collaborator there too. A little side effect that we discovered while we were doing the Princess project is that if you do something like a CGIS-based synthesis where you have to verify whether a solution is correct, you can actually use that to verify whether your existing implementations are correct. So in this domain of operating system ports, like you have some ports already, and once you write the specification, then you ought to be able to check whether your existing code is correct or not. And so that's actually, it's a way we use to debug our specs, but it's also a way to debug the existing code, and you'd be shocked to know that we found bugs. That never happens. Okay, so here's the summary of all the problems that I want your help on. I can't wait for you to all either tweet your results or contact me and we can start working together. I'm not going to make you read all those. I violated Emery's law of text. Forgive me on that. And we have some great sponsors. So thank you to all of them. And most of all, thank you to all my wonderful students and postdocs who make all this possible. So on that note, I think we're open for questions.
Margot, thank you very much for that wonderful talk. It was really tailored towards PLDI, and I really appreciate it. But my question is, supposing you were instead giving a keynote at SOSP or VLDB, or one of those conferences, how much of this material would have made its way into that keynote?
Oh, wow, that's a great question. So I could spend 10 minutes ranting about how I actually get no respect from the SOSP community, but I'll skip that. So I think if I were giving a keynote at SOSP, I would probably have made the focus less on problems I need you to solve and more on advice for the community, because I feel a little better prepared to do that. And the advice I think I would give to that community is operating systems aren't dead, and we are constraining ourselves enormously by being unwilling to actually undertake bold projects to really try to do something novel in the OS space. And I feel like the SOSP community has not embraced that challenge and instead is doing sort of either work whose relevance I can't quite see, or it's like, oh, these are the problems that company X, Y, and Z are facing today, and I want to solve those. So I feel like there's a bit of a more long-term visions thing that we're not doing well. Now, that's a super biased opinion, because that's the kind of problems I like to tackle. VLDB is an interesting thing, because So there's this funny thing that people think of me as a database person. I believe I have published 2 papers in databases in my life. But I happen to have this database company, so therefore I'm a database person. It's a little weird. So I feel a little less, let's see. So I did give a keynote at ICDE that was on non-volatile memory. So I have like those kinds of talks. But if I was giving this talk to that community, I think it would probably be the, look, you need to, like I talk about systems construed broadly, you need to think about data construed broadly. Most data does not live in databases. And we need to embrace that and build systems that are better at handling sort of the messy data that exists in the real world. That's what you get for like 3 minutes of thought. Yeah, that was a really great question. Yeah. Thank you for making me write now 3 keynotes on the spot.
Lovely talk. I wanted to ask for your insight for the PL community about operating system specification.
Mm-hmm.
What's that? So I find operating systems magical. I've never written one. I don't think I could. But when I started to look at their specifications, through some of my colleagues, it's amazing how the safety properties are actually quite weak because operating systems always are allowed to say no. I'd like to open this file. Sorry.
No.
I'd like more virtual memory. Sorry, I can't do that.
Okay, now everyone can hear me.
Okay, so I'll just summarize.
Yeah,
so operating systems are hard, and their security properties are, in some sense, weak because the OS can always say no, which we should all learn to do.
Yeah, the safety properties are very weak. So from a PL person looking at specification and synthesis, right, the file system that refuses to ever create a file is quote unquote correct, right? So there's this whole liveness side of you're actually supposed to try, right? And any thoughts on how we could manage this sort of mismatch?
So actually, I really like that because that tells us a way to get started, right? So the first specification is just say no. Great. And now we have to relax it and sort of try to define what you are allowed to do, right? So, use the file system as an example, and you can imagine specifications that say, you are allowed to do operation X on this file if you can present capability X for that file. So I think you could start to build up some stronger properties. And maybe that's actually a really interesting approach to try rather than trying to codify what we think of as what the OS should do now. So I actually am going to go out on a limb here with exactly 24 seconds of thought that this is exactly the right way to build up OS specifications, is to start to add what we want them to be able to do as opposed to trying to codify what they all do now. Because I think if we try to codify what they all do now, A, we'll be doing it 12 years from now, and B, we're going to lock ourselves in a box. And if nothing else, like I hate boxes. I'm not a cat.
Okay, this time it's on. More questions? If not, Ali has a question.
I had the same problem yesterday.
Hi, I'm Alistair from Imperial College London. Thank you very much for the keynote. I think the open problems you showed us, they look really interesting and really exciting. They also look very challenging from a scale point of view. And I think a difference between the PL and systems community I've observed is that systems people often complain that they have to spend sometimes 2 years building a very big system. There may not be very much novelty associated with a lot of the engineering work needed. And then they try and get one paper published at, I don't know, SOSP, and it probably gets rejected. And then that can be a deterrent to trying. And I wonder, do you have any advice for, say, new professors with a very small research group, maybe 1 student or 2 students? How could they, is it worth them trying to bite off a piece of these problems? Or are these really problems that you need to assemble a team of collaborators before you get going?
That's a great question. So I'll cite 2 people who are smarter than I am. I have a colleague he's now in the VC community actually, that reminded me that scale is a problem you earn the right to solve. And this was more from a company point of view, right? Like if you're launching a company because you think you can scale better than somebody else, it's not exactly necessarily a great strategy because you have to earn the right to demonstrate that you can do something before scaling is a problem. And we don't apply that in research very well. And the other quote that I am forced to bring up is from the Dijkstra THE paper, where, he says that you should pick a problem that is so hard that you can maximize the deep intellectual work and minimize the engineering work. And I think that's really good advice and really hard to put into practice. So if I wanted to do impactful systems work with a teeny, teeny, tiny group, and to a large extent, I spent most of my career with a small group. So not teeny, tiny. I usually had 4 to 6 students, and maybe only 4 who were really working on systems-y stuff. And to be perfectly blunt, I had a dichotomy of projects, right? So it's I'm going to argue for the risk-balanced portfolio of research, which is that you should have one project that is, in my words, fringe lunatic, like bold and daring, that you can at least make steady progress towards, and then having a second backup of sort of the bread and butter that it's like, oh, I can write a fast paper this year. And so that might be the strategy. Big and bold projects are scary, and you end up learning things you didn't intend to learn. And ideally, you can take those and turn those into smaller projects that you really can write up. But you're absolutely right that the bar now for I have a new system that does X, in large part because you have the 50 author Google papers of, oh, and by the way, we've been running it in production for 6 years, right? And we're never going to do that in academia. So a couple of observations are risk-balanced portfolio of the work you're doing, think about the lessons and how those can become papers, and then the other is collaboration. And so figure out who are the industry folks who might actually be interested in this and how can you work with them in a way that is productive. But it's hard. It's super hard.
Let me ask you one of the questions that somebody asked online, which goes back to the earlier part of your talk about asking questions. And this person asked, what if the questions that we fear to be stupid questions really are perceived as stupid questions? So what if the student asks the question to their teacher and the teacher thinks, oh my God, why did I try even to teach this person?
So my first answer is get a new teacher. And I actually mean that sincerely. So I used to teach Intro CS at Harvard, and I really wanted students to ask questions. And I vowed that no student would ever give me a completely wrong answer. This actually makes teaching really fun, because students do, in fact, give wrong answers. And so I think there's 2 things. One is how you respond to those, right? So if you can find a germ of correctness in there, you've identified a really important problem. And then you don't say, you're wrong. You say you've identified a really important problem, and then you give the right answer. And you can do that in a respectful way. And it takes practice, but it's actually super intellectually engaging to figure out how to do that. So I think, when I say find a new teacher, I really mean that. As a professor, my job is not to humiliate students. And if they're asking questions that demonstrate a lack of understanding, then my goal is to figure out how to get them the help to facilitate that understanding. Sometimes I feel like I'm in a minority in my feelings about that. And having had 2 children just finish college and having heard their experiences, as a community, I don't think we're as good at this as we could be. So, a stupid question is really a question of naivete. It's not a stupid question. And, it gets back to when we write paper reviews. You can criticize ideas, but you don't need to criticize people. And I think in some communities we might forget that. How many of you who are faculty and run labs have ever thought hard about establishing and maintaining the culture in your lab? Good. Okay. How many of you thought that was really easy? How many of you actually had any mentoring support to do that? Okay, for those of you who aren't here, I just want to say that, many of the faculty raised their hands and said they think hard about it. None of them raised their hands and said it was easy, and a handful had some mentoring on this. We can do better. So I realized I've had more conversations with my junior colleagues about how to interact with students in the past 6 months than anyone has ever had with me in my entire career. So we can do better.
Hey, thanks, Margot. Are there any more questions? I should say, as an aside, I thought your remark about being permissive with questions is not that dissimilar to the operating system specifications. Be permissive with what you accept. Yes, Oded.
Thanks. So I'm really inspired by the first problem you mentioned about the discrepancy between ML theorems in the paper or the math and the code that ends up running in some GPU, God knows what. So I was wondering, can you give an example of such a discrepancy that how does it actually happen and what, like, I can imagine 1,000 ways it happens, but what's the example you have in mind?
So I actually don't have a concrete example. It's one of the things that keeps me up at night. So for example, I think our code is correct, but our code is premised on the fact that we have all these bounds and that, if we consider splitting a node in a tree and doing so would produce a lower bound that is worse than our best tree, then we prune it. Okay? I think our code is correct, but if we actually do that check incorrectly in any way, we compute the lower bound wrong, we do the check in the wrong direction, we put an equal where we shouldn't, right? We've just eliminated parts of the search space in which the answer lies, and we're going to get a wrong answer. That's really scary. So, we do code audits. Like, we take the whole group, we read through the code, we often record them, and new people look at them. So we try our best. I am reasonably certain few other groups actually do even that. And I don't know of any groups that actually have any formal way to verify those things. Does that help? Okay.
Okay, very good. If there are no more questions, let's thank Margot once again for that wonderful talk.